In this video, we are going to talk about the substitution rule. So the substitution rule is a way of taking antiderivatives of more complicated looking expressions. And so the idea is we have the integral of 2x times the square root of 1 plus x squared dx. And we want to compute this indefinite integral. Now notice 2x is the derivative of 1 plus x squared. Now you might wonder why we're interested in this. Well, 1 plus x squared is sitting right here, and 2x is sitting right here. And so this looks like we may have used the chain rule to get a derivative. Now, as a reminder, the chain rule says if you take the derivative of f of g of x, this is f prime of g of x times g prime of x. And now why this is relevant is this piece 1 plus x squared looks like our g of x, and 2x looks like g prime of x. And so notice, if we pattern match these, this looks a lot like we took the derivative of a composition of things. And now our f of x is just some function that's derivative happens to be the square root function. And so this seems to be the kind of thing that we're doing. And so let's actually write this a bit more formally where I have more space. So, as we said, the derivative of 1 plus x squared is 2x. And so if we pick g of x, it should be 1 plus x squared, just using the notation above. G prime of x would be 2x. And so our g prime of x is sitting right here, and our g of x is sitting right here. And so with our pattern matching, the f prime must be the square root of x, because that's what we've plugged g of x into just to pattern match with this piece of the formula, f prime of g of x. And so we need to know, well, what is f? So we need a function whose derivative is the square root of x. Well, the square root of x is x to the 1/2. And so f of x, we take the antiderivative of x to the 1/2. So that's x to the 3/2 over 3/2 using the power rule, or 2/3 x to the 3/2. And now this is a function whose derivative is the square root of x. And so just from pattern matching with the formula for the chain rule, it looks like we're finding that the integral of 2x square root of 1 plus x squared dx would be 2/3 of 1 plus x squared 3/2 plus c. And so, again, just to see why we're making that claim, we found this side, f prime of g of x times g prime of x. That's our 2x times the square root of 1 plus x squared. And so now our antiderivative is this piece. And so we're like taking the antiderivative of both sides. So this is the integral of f of g prime of x, f prime of g of x. And then this is the integral of f of g of x prime. But that piece would just become f of g because the derivative and the integral undo each other. That's what antiderivatives do. And so the pattern matching just suggests that this must be f of g of x must be what our integral equals, which is what we wrote down above. And so that's kind of the idea of the substitution rule. We're trying to undo the chain rule. And we undo it by pattern matching. And so we just look at this pattern, we figure out what is our f prime, what is our g prime, what is our g, and try to work our way backwards to figure out what f of g of x is, and that gives us our integral. So writing this a bit more formally, the substitution rule says the following. If there are functions f of x and g of x, so that our integral can be written as the integral of f prime of g of x times g prime of x dx then we can write u equals g of x and du over dx equals g prime of x. So du equals g prime of x dx, and substitute this u in to get the integral of f prime of g of x times g prime of x dx equals the integral of f prime of u du, which is f of u plus c, which is f of g of x. Now this all sounds a lot more complicated than it really is. Basically, all this substitution is doing is it's saying we pattern match this expression, we let u be g of x, and then du is going to be g prime of x dx. And that just comes from taking the derivative of u. So if you take the derivative of u, you would get g prime of x, and then you just multiply the dx over in this expression right here. So that's just coming from the fact u equals g of x. And we're basically saying we just want to find the antiderivative of f. Okay, so all of this is basically to figure out what is our f prime, which is what we're doing here. We'll figure out our f prime, and then we take our antiderivative of f prime, which gives us to this step, and then we just plug g back in, which is the step. Because again, u is just a variable that represents g of x. We want to actually know f of g of x. And so the substitution rule's idea is to pattern match to the chain rule, the pieces, and then figure out the antiderivative of f prime. Basically, you're figuring out what f prime is, find its antiderivative, and then plug g back in. Okay, which is what we did up here in this example. We figured out what our g is and what our g prime was. That forced what f prime was, and then we found the antiderivative of f, and then we backtracked, plugging in g into f prime, which is what into f, which is what we did right there. And so we're going to look at some more examples of this. When it comes to the substitution rule, doing examples and practicing this is probably your best option. The more you do this, the more natural it kind of becomes to do. And so first we're going to look at the integral of the square root of 2x plus 1 dx. Okay. Now notice here that we have a composition of functions. If you see a composition of functions, that is a really good sign that the thing you'd want to do is the substitution rule. So to undo take the antiderivative of a composition of functions, substitution rule is usually your best choice. And so the thing we want to pick as u is going to be the thing inside. So it's the thing we've plugged into a function. Well, we've plugged 2x plus 1 into the square root function, so that is kind of the natural choice for u. The natural choice may not always work, but that's the natural choice in this situation. And then we take the derivative. Well, the derivative of 2x plus 1 is just 2. And we rewrite this as du equals 2 dx. You can think of this as like we're multiplying the dx to the other side. That's not exactly what we're doing, but notationally it looks the same. And so that probably is a pretty helpful way of thinking about it. Okay. Now, there's two ways of doing this at this point. At this point, you can sort of insert a 2 into this expression to make 2x show up, which would mean you have to multiply by 2 and 1/2. And so by that, you'd do something like, we have the integral of 1/2 times 2, square root of 2x plus 1 dx. So we have 1/2 square root of 2x plus 1, 2 dx. And then our pattern matching says, oh, look, this is our du, and this piece is our u, so we'd have the integral of 1/2 square root of u du. Okay, that's one way of doing it. I don't particularly like this method of doing it. It does work. The way I like to do this, I like to just solve for dx. And so I'm going to take our expression du equals 2 dx, and I'm going to solve for dx. So I'm just going to divide by 2 to get that dx equals 1/2 du. So I just divided by 2 to solve for dx. And then I plug everything into our integral. So we have the square root of the x squared of 2x plus 1 dx. Well, 2x plus 1 is u, so I have the square root of u, and then dx becomes 1/2 du. Now notice, you get the same expression either way. Okay, it's just a personal preference. I prefer to solve for dx when things get more complicated. I find it's easier if you solve for dx rather than try to kind of work your way into having your du showing up. But either way will work. And so now we want to compute this. Well, this is the integral of 1/2 u to the 1/2 du. And so we want to compute that antiderivative. Well, this is going to be 1/2 u to the 3/2 divided by 3/2 plus c. So we have 1/2 times 2/3 u to the 3/2 plus c. So we get 1/3 u to the 3/2 plus c. And now we need to go back to x, because our actual answer is in terms of x, just to kind of pattern match. What we found here is our f function is 1/3 x to the 3/2 plus c, plus a constant. And so what we've done here is basically we found our f. But we want f composed with g, and so we're going to plug g back in. And so our actual answer to the integral of the square root of 2x plus 1, it's going to be 1/3, and then our u is 2x plus 1, so we're going to have 1/3 2x plus 1 to the 3/2 plus c. And so that then is our indefinite integral. Remember, indefinite integrals always end with a plus c, a constant at the end. So that's why I brought the plus c in all of these. Okay, and so that's kind of the steps in this one. Is we looked for a composition. That the inside function is what we picked to be our u, or inside function, and then we kind of ran with it. Okay, and important thing to note here is we didn't actually have du just sitting there. We kind of had to manipulate it to make du show up. That is normal. As long as you're only off by a constant, that's totally fine. If you're off by more than a constant, you run into problems because you can't multiply by x and 1 over x. That's an issue. But you can multiply by constants, and so we can multiply by like 2 and 1/2. And so as long as you're off by only a constant from your derivative, you're fine. If you're off by more than a constant, then you have issues. And we'll talk about that in a minute as well. So next, we're going to take the integral of x over the square root of 1 minus x 4x squared dx. Okay, again, we're going to look for a thing that's inside that we've done some kind of composition with. That is the dead giveaway for a u-substitution, or the substitution rule. And so the thing that it looks like we plugged in is our 1 minus 4x squared into the square root function. So u is going to be 1 minus 4x squared. That appears to be what we're doing here. Well, then du is going to be equal to minus 8x dx, just taking the derivative of 1 minus 4x squared. And then, just as a reminder, I like to solve for dx, so dx is negative 1 over 8x du. And so now we're going to plug that all in. And so plugging that all in. Now when you plug it all in, I leave the x's there, and then I look for cancelization. So I have x over the square root of 1 minus x to the 4x squared. Well, that's u, so I have square root of u. And then dx is minus 1 over 8x du. And I notice I have an x here, and I have an x here. And so I'm left with the integral of minus 1 over 8 square root of u du. Now, just to kind of give you the idea of the pattern matching way of doing it, this is the last time I'm going to do the pattern matching way. But in the pattern matching way, you take this one and you say, oh, well, I have an x already, so I need to multiply by negative 8. So I need to have a negative 8x on the top. Well, what do I have to multiply by? That, because I multiplied by negative 8, I have to multiply by negative 1/8 as well to undo the multiplying by negative 8. And then I just have my du sitting here. And then I had to multiply by the negative 1/8 to make my du show up. And so either way, you end up with the same expression. I prefer the whole solve for dx method. But either way will work. We get the same integral in the end. And that integral is, we want to take the integral of negative 1 over 8 square root of u du. Well, this is going to become negative 1/8 times the integral of u to the minus 1/2 du. So we have negative 1/8. U to the minus 1/2, using the power rule, is u to the 1/2 divided by 1/2. You add 1 to the exponent, divide by the new exponent. Then we're going to multiply by a constant. Dividing by 1/2 is the same as multiplying by 2, so we'll get negative 2 over 8 u to the 1/2 plus c. So we got negative 1/4 square root of u plus c. And now we have to plug our u back in. So we get negative 1/4 the square root of 1 minus 4x squared plus c. And that is our indefinite integral, or antiderivative. Okay, now one thing to be aware of is you can always check your answer by taking the derivative. So once you get to the very end, if you want to check, did I get the right answer? You can just take the derivative of your answer and see what you get. So if we take the derivative of negative 1/4 square root of 1 minus 4x squared plus c, well, we're going to have to use the chain rule here. So we have negative 1/4 times the derivative of the outer function, it's going to be 1 over 2 square root of 1 minus 4x squared, times the derivative of 1 minus 4x squared is negative 8x. So multiplying this out, we have negative 1/4. I keep writing that backwards. Negative 1/4 times 1 over 2 square root of 1 minus 4x squared times negative 8x. Well, here, these combine to give us 8, so they negative 8, so we have 8's cancel, and we're just left with x over the square root of 1 minus 4x squared by simplifying. And notice that's what we started with. That was what we were finding the antiderivative of. The plus c gets killed in the derivative because constants go to 0 in derivatives. And so we see from taking this derivative, we do get the thing we were finding the antiderivative of. So we got the right answer. Okay. So next, let's look at one more example. So we're going to take the antiderivative of tangent of x. Okay, so we want to find the antiderivative of tangent. You might think, well, this is not a composition of functions. And you'd be right, but we can write this as the integral of sine of x over cosine of x. And again, doesn't really look like we've got a composition here. But the trick is here, well, we don't have a composition, we do actually have a derivative sitting there. Remember, sine and cosine are derivatives of each other. And so we are going to essentially resolve this issue by making use of that fact. Now, you could pick u to be the sine or cosine, but if you pick it to be sine, which is what I'll do first, just so you can see what will happen, we run into a bit of an issue. You can get around the issue, but it's really probably preferable if you don't run into it. So if I picked u to be sine, and again, I'll do this in red just to make this clear. If I pick u to be sine of x, then du would be cosine of x, dx, and then dx is going to be 1 over cosine of x du. So when I plug things in, I'd have the integral of sine of x becomes u, so u over cosine of x dx. But I want to replace dx, so I get, and then du over cosine of x. So I'd have the integral of u du over cosine squared of x. And now this is where the issue comes up, in that cosine squared of x is kind of a problem because it's not in terms of u. You can't take the antiderivative until you're only in terms of u. And so picking u to be sine of x runs into this issue. Now, you can resolve it. I'm not going to do it this way, but if you want to resolve it, you get u du. You can change cosine squared into 1 minus sine squared. And we know that we have u du over 1 minus, but sine is u, so this would be 1 minus u squared. And so we could take the derivative of u over 1 minus u squared, the antiderivative of u over 1 minus u squared. And we get the same answer as what we do if we just pick u to be cosine. So we're going to just pick u to be cosine because it simplifies things a lot. And the hint of why this is a good selection is when you take du, you'd get negative sine of x dx. And notice, sine of x dx is sitting inside of the thing we're taking the antiderivative of. So we're just off by a negative, which is really great. And so that's a good sign that u being cosine is a much better choice. But you can make it work the other way. And then dx is going to be negative 1 over sine of x du. So now plugging things in, we have sine of x is u divided by cosine, sine of x is not u. So sine of x divided by cosine is u times dx is negative 1 over sine of x du. Well, our sines cancel. And we're left here with the integral of negative 1 over u du. That is a u, not a 4. Okay. Well, we know how to take the antiderivative of 1 over u. So this is negative ln of u plus c. And we want the absolute values because remember, we want to take the largest possible domain. And so the absolute values give us the largest possible domain when taking an antiderivative of 1 over u to make sure its domain's the same as the function 1 over u. And so now from here, we just need to plug our u back in. So we get negative ln of cosine of x plus c. And so what we found is the integral of tangent of x is negative ln of cosine of x plus c. And so we were able to compute that antiderivative. Okay, and so we didn't know the antiderivative of tangent before this, but now we do. And so this is kind of one thing to be aware of, is with trig functions, because they kind of have pattern matching in their derivatives, even if you don't have a composition, you still can possibly make u-substitution work. Okay? And so now we're going to go into something I kind of did before. I alluded to it in this piece right here. But sometimes when you do a substitution, some of the x's don't disappear. And sometimes that's a problem, sometimes it's not. You can make it work, though. If you made a good substitution that actually can work, you can still make it work. But typically, you don't want to use a different x, or a different choice of u, unless it was coming from a composition. And that'll make more sense, hopefully, with this next example. So next, we want to take the integral of the square root of 1 plus x squared, x to the 5th dx. Okay. Now, it's very clear that we've plugged 1 plus x squared into the square root function. And so that is our natural choice for our u. U is going to be 1 plus x squared. Then du is going to be 2x dx. So dx is 1 over 2x du. Okay, so that's just the same pattern we've been following with substitution so far. And so if we plug things in, we have the integral of the square root of u, because 1 plus x squared is u, x to the 5th times dx is 1 over 2x du. Okay, well, we can cancel this x with one of those x's to leave us the integral of the square root of u x to the 4th du. Well, we have a mixture of u and x's now. You can never take the antiderivative wall that's still a mixture of u and x's. Okay, so you have to get rid of all the x's before you can take the antiderivative. And so at this point, you might wonder, well, we've got a problem. But what we're going to do is we're going to use what we know about u to get rid of the rest of the x to the 4th. And so we did this up here. Here, I said, well, I know that sine is u, and so I replace sine squared with u squared. Okay, I'm going to do basically the same trick here. I know that u equals 1 plus x squared. So x squared must be equal to u minus 1. Squaring both sides, I get x to the 4th equals u minus 1 squared. So that tells me how to write x to the 4th in terms of u. So this becomes the integral of the square root of u times u minus 1 squared du. Okay, and so now we're just going to multiply this out. So if we multiply this out, it'll become just a series of power terms, and we can take the antiderivative of each of those using the power rule. So we have the square root of u, which is u to the 1/2, times u squared minus 2u plus 1. So we're going to have u to the 2 plus 1/2 is 5/2, minus 2u to the 3/2, plus u to the 1/2 du. Now we need to take the antiderivative of each piece, so we're going to use the power rule for each piece. I lost my 1/2. There was a 2 here, so I'm just going to put the 1/2 in front of everything. Remember, you can pull constants out in front, so it's not particularly relevant. Just make sure you lose your constants partway through. I just noticed that I had. So we're going to have 1/2 times, take each of these antiderivatives using the power rule. So we have u to the 5/2, that becomes u to the 7/2 divided by 7 over 2, minus 2u to the 5/2 divided by 5 over 2, plus u to the 3/2 divided by 3 over 2, plus a constant at the end. So we have 1/2 times 2/7 u to the 7/2 minus 4/5 u to the 5/2 plus 2/3 u to the 3/2 plus c. Now multiplying our 1/2 through everything, we're going to have 1/7 u to the 7/2 minus 2/5 u to the 5/2 plus 1/3 u to the 3/2 plus c. But now we need to plug our x back in. And so remember what u was. U is 1 plus x squared. So everywhere I see a u, I'm going to replace it with 1 plus x squared. So I have 1/7, 1 plus x squared to the 7/2, minus 2/5, 1 plus x squared to the 5/2, plus 1/3 times 1 plus x squared to the 3/2 plus c. And that then is our function. Now notice that is a fairly complicated looking function, but we did find the antiderivative. If you take the derivative of this, for sake of time, I'm not going to, but if you took the derivative of this, you'd find it does simplify to the square root of 1 plus x squared times x to the 5th. Okay, so now what we want to do is we've been doing antiderivatives here. Now we want to shift gears a bit and talk about how do we do definite integrals. And so for definite integrals, there are two methods of doing this. Okay, I'm going to mention the first, and then I'm going to mention the second. So I'm going to first do an example with the first method. Okay, so method 1 is find the indefinite integral and then compute using the fundamental theorem of calculus part 2 after. So this is the first method. You can compute the indefinite integral, do all of that we've been doing, and then just plug the bounds in, basically. And so we're going to do an example of that. So we want to take the integral from 1 to 3 of 3x squared times the square root of x cubed plus 4. Okay, so we want to compute this definite integral. And so we're going to do the exact same thing. We're basically going to ignore the fact we have bounds, and we're just going to compute the indefinite integral of 3x squared square root of x cubed plus 4. Okay, well, just doing that, we have u. The thing will look like we've plugged in as x cubed plus 4. So x cubed plus 4 is a good choice for u. Du is this going to be 3x squared dx. And then dx is going to be 1 over 3x squared du. So plugging everything in, we're going to have 3x squared square root of u, because remember x cubed plus 4 is u. And then dx becomes 1 over 3x squared du. And these two cancel. So we're left with the square root, the integral of the square root of u du, which equals, we've done this a few times. So the integral of u to the 1/2 du, so we get 2/3 u to the 3/2 plus a constant. So that whole thing is our antiderivative, other than we have to plug in what u is. So u, remember, is x cubed plus 4. So you do still have to plug that in. Okay? And so now from here, what we can do is we say, okay, I know the antiderivative. Now I'm going to use the fundamental theorem of calculus. And so that all was to find the antiderivative. This then tells us, well, we know the antiderivative is 2/3 x cubed plus 4 to the 3/2. Remember, the plus c isn't really relevant, so I'm not going to write it down. And we go from 1 to 3. And so we just plug things in. So we're going to have 2/3 times 3 cubed plus 4 to the 3/2 minus 2/3 1 cubed plus 4 to the 3/2. And now this has a pretty nasty answer because I made it up on the spot. We're going to have, here we're going to get 2/3 times, well, 3 cubed is 27, so we're going to have 31. We have 27 plus 4, which is 31 to the 3/2, minus 2/3, and then 5 to the 3/2. And that number, that is a number, is then our answer to our definite integral. Okay, and so that's the first method. We just do everything we were doing before, And then after we've found the antiderivative, meaning gone back to x and everything, we then just plug in the bounds. Okay? So now we're going to mention the second method. So method 2 is basically change the bounds to be in terms of u. Then don't go back to x. Just solve in terms of u. Okay, now the actual theorem behind this is the following, and we will do some examples of this as well. So if g prime is continuous on the closed interval a to b, and f is continuous on the range of u equals g of x, then the integral from a to b of f prime of g of x, g prime of x, is equal to the integral from g of a to g of b f of u du. Okay, so basically what we're saying here is that if we know that we've got a function that's continuous on a to b, and the f is continuous on the range of g, which that's not really saying a lot. Basically, this is saying f of g is a continuous function on the whole interval a to b. That's basically all we're saying here, is just that f of g is continuous. And if that holds true, then the definite integral from a to b of f prime of g of x, g prime of x, which again, that's just the result of the chain rule, is equal to the integral of g of a to g of b of f of u. And so we can just plug a and b into our function g, basically, and use those as our new bounds. And so let's look at some examples of actually doing that, just to make it a bit more clear what we're saying here. Okay, so we want to find the integral from 1 to 2 of dx over 3 minus 5x squared. Okay, so once again, we start by finding our u. So u is going to be the thing we look like we've plugged into something. Well, that looks like 3 minus 5x. So u is 3 minus 5x. Du then equals minus 5 dx. So dx equals negative 1/5 du. So now this is where the change comes in. The change is we need to figure out what u is in terms of x. So we're going to plug our bounds into our u function as well. So when x equals 1, u equals 3 minus 5 times 1, which is 3 minus 5, which is negative 2. And when x equals 2, u is 3 minus 5 times 2, which is going to be 3 minus 10, which is negative 7. And so our bounds are going to be negative 2 to negative 7. And so when we plug everything in, we get our bounds get changed to negative 2 to negative 7. Now the order is important here. So we plugged 1 in and got out negative 2, so negative 2 is on the bottom. We plugged 2 in to get out the negative 7, so negative 7 is on top. And then we have our dx is going to become negative 1/5. I'm going to actually write it like this. We're going to have 1 over, and this is going to be u squared, times dx, but dx is negative 1/5 du. So we have the integral from negative 2 to negative 7 of negative 1 over 5 u squared du. Okay, so that is now what we want to compute. It's just that expression, and so I'm going to write it down here. Okay, well, pulling our negative 1/5 out, we have negative 1/5, the integral from negative 2 to negative 7 of 1 over u squared du. But remember, 1 over u squared is the same as u to the minus 2. So this is going to give us then negative 1/5 times, we're going to have u to the minus 1 over minus 1 from negative 2 to negative 7. Okay, and so this then is negative 1/5 times negative 1 over u from negative 2 to negative 7. Plugging in our bounds, we have negative 1/5 times, we're going to have negative 1 over negative 7 minus negative 1 over negative 2. So we have negative 1/5 times, we're going to have 1/7, then minus 1/2. Getting a common denominator, we're going to have negative 1/5 times, we're going to have 2 over 14 minus 7 over 14. So negative 1/5 times negative 5 over 14. And now when we multiply that through, we get 1 over 14. And so that whole definite integral becomes 1/14. Okay, and so kind of the steps here are that we just have the additional step of finding what the bounds are, and then we just plug in the bounds. So notice here, we plugged in the bounds in terms of u. That is the main place where these methods differ. In method 1, we went back to x and then plugged the bounds in terms of x. In method 2, we stay in terms of u. Okay, in reality, they're fairly comparable. I think method 2 is slightly faster because you don't have to do the step of going back to x. Okay, that is basically the only difference, because you'd still end up computing these values later on anyway. You end up computing those values when you go back to x and then plug the bounds in. The same computations show up. And so the only real benefit of method 1 is it's less to remember. You're just finding the antiderivative, then doing the bounds. With here, you have to remember to change the bounds. But you do have to remember to change the bounds if you use method 2. The bounds do have to be in terms of u. Okay, so let's look at another example. So I'm going to take the integral from 1 to e of ln of x divided by x. Okay, this is another one of those where it's like, well, we don't have a composition really here, but we do have a function and its derivative showing up. So there's kind of an obvious choice here. Our u is going to be ln of x because its derivative is showing up. Du is going to be 1 over x dx. So dx equals x du. And now we need to change our bounds. So when x equals 1, u is equal to ln of 1. Well, ln of 1 is 0. And then when x equals e, u equals ln of e, which is 1. So our bounds are going to be 0 to 1. So we're going from 0 to 1 because of our new bounds. Ln of x is u, and divided by x times dx. Well, dx is x du. So we're left with the integral from 0 to 1 of just u du. So that's our result from plugging in our bounds. And so we're then going to have u to the squared over 2 from 0 to 1. And this then just becomes, we're going to have 1 squared over 2 minus 0 over 2. So we're left with 1/2. Okay, so this one is pretty straightforward. Hopefully that all makes sense with what we did here. Okay. So now let's look at another example. So next we're going to take the integral from 0 to 10 of 2x e to the x squared dx. Okay, so look for a composition. Our composition, we've plugged x squared into the exponent of e. So the function e to the x is a function, and we've composed x squared into the exponent. And so our u is going to be x squared our du is going to be 2x dx. Notice that's just sitting there, but I'll solve for it like I normally do. So dx equals 1 over 2x du. And now changing the bounds, with x equals 0, u is going to be equal to 0 squared, which is 0. And if x equals 10, u is going to be equal to 10 squared, which is 100. So our bounds will get changed to be 0 to 100. Now plugging everything in, our bounds go 0 to 100 now. We have 2x e to the u, because x squared is u, times dx, which is 1 over 2x du. The 2x's cancel, and we're left with the integral from 0 to 100 of e to the u du. Which is then just going to be e to the u from 0 to 100, because the antiderivative of e to the u is e to the u. So I get e to the 100 minus e to the 0, which is going to be e to the 100 minus 1. Okay. And now another example to look at is, let's look at the following. So now we are going to take the integral from 1 to 4 of e to the square root of x divided by the square root of x. Once again, the square root of x looks like it's the thing that we have plugged in here. So it looks like that's our composition. So our u is going to be the square root of x. Du is then 1 over 2 square root of x dx. Which I'm going to rewrite that as 1 over 2u dx, just to be clear. So then dx is equal to 2u du. The reason why I'm doing this is because we know the square root of x is just u, so I'm just replacing it to begin with. Now when x equals 1, well, we're going to have u is equal to the square root of 1, which is 1. And when x equals 4, u is going to be the square root of 4, which is 2. So this now becomes the integral from 1 to 2 of e to the square root is u. The square root of the x becomes u. The square root of x in the bottom also becomes u. And then dx is 2u du. Notice all u's cancel, and we're left with the integral from 1 to 2 of 2 e to the u du. And now we just have to compute this, which is, its antiderivative is going to be 2 e to the u, and we're going from 1 to 2. And so plugging in our bounds, we have 2e squared minus 2e to the 0. So we have 2e squared minus 2. Oh, it's not e to the 0, it's e to the 1. So e to the 1, so we get minus 2e. And that is our answer there. Okay, and so from all of this, what we see is that we can just change the bounds to compute these definite integrals. The reason why I only did one example of method 1 is method 1 is the same as what we were doing all along. So you just find the antiderivative, pretending like you didn't have bounds, just do the definite integral all without caring about the bounds, and then you just, after you have that, you plug in the bounds. And so because of that, I thought focusing on method 2 is more useful, because method 1 is really just doing the same thing we were doing before, and then plugging in bounds. We're here doing some practice plugging in bounds. I think it's helpful.